Hello everyone and welcome to my channel. So today we have a question for the given molecule X. So we have a molecule X. Okay. The preferred site for the attack of the electrophile is. So we have to find the preferred site for the electrophilic attack. So as you can see this structure, we have two aromatic rings and in between we have some functional groups. So basically we are being asked about the electrophilic aromatic substitution reaction. You can see the sites are labeled as R, P, S and U. And amongst these four sites, we are being asked to determine which should be the preferred site for the electrophilic attack. We will take one ring at a time. Let's say this is the left hand side benzene ring is the ring 1 and the right hand side benzene ring is ring 2. Let's label it like that. So I have made this ring 1 with its substituent. So you can see here that the substituent on ring 1 is CONH-PH. Okay, CONH-PH. So we have a CO, then we have an NH and then we have a pH. pH means the second ring, second aromatic ring, the phenyl group. But which one is the immediate group which is attached to the aromatic ring? So the immediate group, the nearest group which is attached to the aromatic ring is the CO group, okay, the carbonyl group. And we very well know that the carbonyl group is the electron withdrawing group. Its nature is electron withdrawing according to -I and -R effects. So inductive effect as well as resonance effect. So both of these indicate that carbonyl group is electron withdrawing group. So through resonance, okay, so since oxygen is the highly electronegative atom, so it will withdraw electrons towards itself. And these ring electrons are delocalized more towards the oxygen. So it develops a partial negative charge, delta negative. So it is electron withdrawing through resonance as well as -I effect, the inductive effect. Inductive effect also because oxygen is much more electronegative than carbon, so it will have a tendency to withdraw electron towards itself. And what is the result of this? Because of this electron withdrawing nature, this is also, the carbonyl group is also ring deactivating. So carbonyl group is, because of its electron withdrawing nature, it is also ring deactivating towards the electrophilic aromatic substitution. And this is the reason that it will not support the attack of the electrophile. Thus, electrophilic attack is not favored in case of the carbonyl group which is attached to the aromatic ring. And we see the given sites in ring 1. So we are discussing ring 1, this ring. So the given sites are R and P here. Okay, R and P sites. So R and P sites are not the favorable sites for electrophilic attack. Now let's check ring 2. Okay, now you can see I have drawn the groups, the functional groups which are attached to ring 2. So the right hand side benzene ring was our ring 2. And near to the ring 2, we have NH, CO, PH. PH is our phenyl group which was our ring 1 on the left hand side. So we have indicated it as PH group, okay, the phenyl group, the first ring. Okay, so you can see here NH, CO, PH is the group which is attached to the second ring. And now which one is the group which is immediately next to the second benzene ring? So the functional group which is immediately next or which is attached directly to the benzene ring is the NH group. And we very well know that in the NH group, nitrogen has lone pair of electrons, okay? And these lone pair of electrons are delocalized onto the benzene ring. That means nitrogen, the NH group, is electron donating towards the aromatic ring. And this electron donating nature is because of the resonating effect, not the inductive effect. Through inductive effect, it is electron withdrawing because nitrogen is more electronegative than carbon. But through resonance effect, this is electron donating towards the ring, and this resonance effect is much more dominant than the inductive effect in case of the benzene rings or any pi conjugated molecule. So NH group is electron donating group by resonance effect, also known as the mesomeric effect, that you must have learned in your basic organic chemistry classes. However, one more thing is to be noted here, that this lone pair is slightly delocalized onto the this carbonyl group as well, but some of it also goes to the benzene ring. So that this delocalization towards the carbonyl oxygen, we will not consider it right now. We will only focus on the part where it is electron donating towards the benzene ring. Now, since NH group is electron donating towards the benzene ring, that means it is ring activating, right? It is ring activating towards electrophilic aromatic substitution. That means it will favor the attack of the electrophile. And the ring activating groups which are electron donating towards the benzene ring, you have read this, you know this, that these are ortho-para directing groups, which are ring activating groups. Okay, so the preference will be the ortho-para positions. And we are being asked about these two. So we have S, the site S indicated by letter S, this site S and site U. Both of these have been given, and we have to identify which one should be the preferred site for the electrophilic attack. Okay, so S is the ortho site. As you can see, it's in the ortho position. So S site is ortho site, while U site is the para site. So if you see the position of the functional groups, you can see the ortho position is quite hindered. So this group, this big group is near to the ortho position. So it is the ortho position is a bit sterically hindered because it contains NHCO pH groups. Okay, it's near to the NHCO pH groups. So ortho position will be the second preference. Para is quite free. There are no functional groups, no steric hindrance near the para position. So this para position or the U site, the site indicated by letter U, should be the most preferred site for the electrophilic attack. So let's check our options. So it's given predominantly at R, no. R and U, no. Both para positions, R and U, no. P and S, both ortho positions, no. Predominantly at U, yes. The electrophilic attack, the attack of the electrophile is predominantly at U. So U site is the most preferred site for electrophilic attack because it has least steric hindrance, and moreover the group which is attached to this benzene ring is the ring activating NH group. So our answer will be option 4, predominantly at U. Now if in this question, if the question is asked in a different way, and if say, just imagine if we are being asked that what should be the order of the electrophilic attack according to the most favorable to the least favorable. If the question is asked in this manner, then how you will order these 4 positions R, P, S, U. Okay, so we have seen that this ring 1 is attached to the substituent which is electron withdrawing. So that means it will be favoring the meta position, not the ortho-para position. So this will R and P will come later. So initially S and U, the ortho-para positions, and in S and U, among S and U, we just saw that S position, the ortho position, is sterically hindered. So the most preferred one will be U. So U will be most preferred, followed by S because it is electrophilic attack. So the ring activating substituent, that is NH, is preferred. So ring 2 will be preferred first, and in ring 2, U site, the para site, will be preferred, followed by the S site, the ortho site, which will be preferred over to the, then we will move to ring 1, okay, which has electron withdrawing substituent towards it. And among R and P, again R will be preferred first, followed by P. Okay, so para again will be preferred, followed by the ortho in ring 1. So this should be the order of reactivity of the electrophile. So I hope you understood this explanation, and if you have any doubts, please write to me in the comment section. And please do not forget to like, share and subscribe. And till then, keep learning, keep watching, and see you soon with the next problem.